Good morning, everyone. We are going to start the program in next 5 minutes.
Hello.
लेटेस्ट वाला प्रोग्राम है
मेरे को भी करवा दिया
अच्छा हम रखते हैं
आपने
मैं ही रखे रहता हूँ और तुम्हें इधर आओ
Knowledge is
या
the
जाओ
light
बच्चों के
that
साथ
guides us to
मैं आता
innovation,
यार ये
and
हमेशा बच्चे
innovation is
जैसा
the key that unlocks a sustainable future. Let's ignite this spark of curiosity today and shape the world of tomorrow. Welcome to CANDEE 2024, where every spark of brilliance illuminates a sustainable future. Good morning, distinguished guests, respected dignitaries, esteemed speakers, faculty members, and participants. A very, very warm welcome to this absolutely wonderful, beautiful, and auspicious day that brings together so many special people like you. I, Vani Gagil, have the pleasure of being your hostess for the evening. Today, we gather here not just as professionals, researchers, and academics, but as a community united by a shared vision. A future where innovation in nanomaterials and energy efficient devices creates a sustainable world for generations to come. Before we begin, on behalf of the organizing committee, I would like to extend my heartfelt thanks to each one of you for gracing this event with your presence. Your participation is what makes the conference not just an academic gathering, but a vibrant exchange of ideas, inspiration, and collaboration. This gathering is a testament to the collective passion, innovation, and dedication of some of the brightest minds in the fields of technology and sustainability. Today, as we come together under one roof, we aim to explore groundbreaking ideas and solutions that can shape our future and for all of us. We are deeply honored to host these distinguished scientists, researchers, and thought leaders from across the globe. Your groundbreaking contribution to the fields of energy and environmental sciences inspire all of us to push boundaries and redefine possibilities. A special thanks to our esteemed organizing committee, volunteers who have worked tirelessly behind the scenes to bring this conference to life. Your dedication has ensured that CANDEE continues to shine as a beacon of excellence. As we embark on this scientific journey, let us not only explore new frontiers in nanotechnology, but also foster collaborations that can help shaping a sustainable and energy efficient future for our planet. So, let's inspire us as we embark on a day filled with insightful discussions and inspiring keynote addresses. Thank you everyone for being here with us today. Now, we'll take the session forward by taking the blessings of our God and lamp lighting ceremony. Now, I would like to request esteemed director AVP Triple Item Gwalior, Professor S.N. Singh, Professor Rajiv Ahuja, Director IIT Ropar, Professor Aparao, Robert A. Women Enrolled Professor, Clemson University, Professor Ajay Kumar Mishra, Department of Chemistry, University of the Western Cape, Dr. Ajay Kumar, HOD Engineer Sciences, and Professor Anurag Srivastav to come on the dais and join us on the highly anticipated inauguration ceremony of CANDEE 2024. It is believed that lighting a lamp fills the atmosphere with positivity and tranquility. As we seek the blessings of the universal divine power to guide us toward a fruitful day, let us come together to make this movement truly meaningful. Lighting the lamp is a time-honored tradition in our cultures, representing the removal of darkness, the enlightenment of knowledge, and the victory of wisdom over ignorance. So let us take a moment to celebrate the spirit of collaboration and innovation that bind us all in this pursuit of progress. To formally begin the proceedings, I request our esteemed guests to occupy the chair and grace the stage with your presence. Every gathering is made special by the presence of extraordinary individuals. Now, I would like to request Professor Anurag sir to kindly come forward and warmly welcome to our all esteemed guests as we celebrate their presence with us today. Welcome, sir. As Albert Einstein once said, quote, the important thing is not to stop questioning, unquote. With the spirit of curiosity and innovation, we look forward to an enriching experience at this conference. Now, I would like to invite Anurag sir to share his insights and give us a brief overview of CANDEE and this prestigious international conference. Welcome, sir.
Thank you, Vani. Very good morning, one and all. Present in this August gathering, esteemed guests on the dais, my own mentor and today's chief guest of this inaugural ceremony, Professor Rajiv Ahuja. I did my postdoc with him. Our director, Professor S.N. Singh, the great motivator behind whatever I am doing here in Triple in the last 3 years. My other collaborator, Professor Apparao from Clemson University, USA. Another colleague of mine, very good scientist and very good friend, Professor Ajay Mishra from South Africa. My head of the department, Dr. Ajay Kumar. And esteemed speakers who have joined from different parts of the world to this CANDEE 2024, the third version of this series. Of course, the participants are very, very important part of this ceremony and this event and making this successful. So I welcome all the participants as well. I welcome the other dignitaries who have joined this program from different organizations, Shiksha Sanskriti Uthanyas and others, who have joined us, people from media and my own faculty colleagues and students. Very, very good morning and warm welcome to all of you. I've been asked to brief about this program. So I always feel pleasure, as I said, welcoming you all to this third edition of the International Conference on Advances in Nanomaterials and Devices for Energy and Environment. The first edition of this conference was organized in 2019 and it was not named CANDEE. So the name, the credit goes to Professor S.N. Singh, who coined this name CANDEE, and earlier it was actually iCANDEE. So second version with CANDEE, it was in 2023. And this event was announced in August first week, so it's almost 4 months completed from the announcement, and the result is in front of you. Thank you all for accepting and joining us. I'm very happy to share that, particularly for this conference, we have received more than 200 abstracts, and out of that we have accepted 102 abstracts, and finally registered are 84. And out of 84, 14 are oral presentations, 64 poster presentations, and 5 are thesis presentation awards. Among these speakers, 4 keynote talks, 4 plenary talks, 37 invited talks, and 3 short invited talks. You can see from the program schedule, it's almost packed, jam-packed. There are 19 overseas speakers and 29 from Indian institutions, and there are 11 are online sessions of the speakers from outside India. IIIT body was established in 1997 with its vision and mission as imparting IT-enabled education to youth and making them entrepreneurial, socially and globally acceptable. We have 5 departments in the campus, and ours is Engineering Sciences Department is one of them, focusing more on strengthening the base of these students, especially in the fundamentals to advanced sciences, especially in the niche areas of material science and mathematics. Campus is spread in 160 acres of land divided into 2 pockets, pocket A and pocket B, and total number of students in the campus is around 15,000, getting nurtured through 65 full-time faculties and number of visiting and adjunct faculties from different Institute of Excellence in India. The institute has a very good alumni base of around 4,500 alumnus, part of almost all the big IT and management companies in India and abroad. Around 100 startups and more than 150 entrepreneurs in different sectors have been nurtured so far from this campus in the last 26 years of journey. In the last 2.5 years, the institute has seen an overall exponential growth, and for that we thank our esteemed director Professor S.N. Singh. Since last year, the organizers have started to appreciate the efforts of our esteemed director, and you'll observe that we are going to honor 3 scientists. So last year in CANDEE 2023, Professor Rajiv Ahuja couldn't come in person, so we felicitated him. So we feel that it is an honor for us because he's here in person, we can consider once again here. And two other dignitaries, I'll read those citations, Professor Apparao and Professor Ajay Mishra is here. So for the proceeding, I invite Ruani. Thank you. Thank you very much.
Thank you, sir, for giving us a comprehensive overview of CANDEE 2024. As we move forward, remember, the future belongs to those who believe in the beauty of their dreams. Somewhere, something incredible is waiting to be known. May this book serve as a beacon of inspiration and fundamental for future discoveries. Now, I kindly request to our esteemed guests to do the honor of unveiling this significant work. Let this unveiling symbolize the beginning of yet another chapter in the legacy of CANDEE, lighting the way for innovation, sustainability, and progress. Thank you, everyone. Leadership and learning are indispensable to each other. We look forward to the inspiring words to guide us through this remarkable event. Let us welcome with a big round of applause Professor S.N. Singh, the esteemed director of ABB IIIT Gwalior, to share his words of wisdom.
Good morning to all of you. The people sitting on the dais, well-known outstanding researcher, good administrator, Professor Ramjaji, Director IT Department, Apparao, a good scientist, good professor, and very known researcher, as you can see his citations. Mr. Raji from Africa, and both sides are faculty colleagues. One is the head of department, Dr. Ajay, and another is our dean, as well as the chief creator of this CANDEE 2024, the Inaugral class. My faculty colleagues, other guests, like a person from Berkeley, Dean Pharmacy from India and his team, and also other people like Sichandas, people from again from Science College, Gwalior, and delegates and faculty members. No doubt, this started 3 years back, especially when I joined. Then I tried that any institution should not only distribute the degree, making examination, teaching, and distributing. We should also do some extracurricular, and also dissemination of the knowledge is also very important. Then I asked the people, organize the workshops, organize the conferences, organize the various other activities, symposiums, seminars, all the things we started. And now it is in such a way that I can tell you in the 2024, we organized more than 50 workshops. More than 50, that is a limited faculty. We are at that time we are having only 40 or 50 faculty, now it is 65. So they were all the faculty almost they organized, each departments are organizing, and every year we are at least 4 workshops, international conferences we are organizing. So that is basically part of any academic institutions of excellence that they should do, apart from the academic research and the dissemination of the knowledge also to be there. This institute, no doubt already told, that's started long back. It has crossed 27 years because no doubt the laying stone was done here in 1996 on the 17th of January, where we celebrate our foundation day. But the government approved this college, that institute. It was in 1997, and first batch started in July 1998. So you can see from there onwards, and the main theme of this institute, no doubt IT is there and management was there. It was IT-enabled management concept was there. And it was started with the 5-year degree, not even the 4-year degree. And that was an integrated program where we give the BTech plus MTech in IT or BTech IT plus MBA. These were the genesis. And it started later we added the computer science as the demand of the nation. And last year we added the IEEE, the electronics and electrical engineering, that is electronics oriented because that is also a part aspect. Then we added this is the other programs like mathematics and scientific computing in the mathematics department, that we say it is not mathematics department, it's a engineering sciences. Because sciences will come all the sciences, whether that is justly included in this engineering applications. And we have the MTech program. This year also we are going to increase the strengths as well as various MSc programs as well as the MTech programs in this institute. So this is the journey, and this institute has picked up, and I hope it will go in the long way, and we will see it will fly the course. Now coming to this conference, you see they are talking about the nanotechnology, and they are saying that it is the conference advanced technology and devices for energy. Whenever any nation, the development is indicated by the what is the concept of energy. Energy is the basis. Without energy, nothing will happen in the world. Even though we work with energy, in human being, whatever you can say is energy. So the energy is the basic parameter. And once you are to extract the energy and take more and more energy, the environment will be affected. The progress and the perfection both are the complementary, contradictory opposites. If you are progressing, the sustainability is the question. So always we are talking about the sustainable development, environmental regulations, all the things are coming once we are progressing. And the progression is the part of the life. Everyone has to progress. Every system has to progress. Whole world has to progress. So along with this various technological advancement and the material science, I believe, although I'm not from material science, but material has played a very vital role. Whatever the computing you see, it is a material. The chip you see, it is a material. How we are organize this material, it is doing the task and then giving up. Computer science, it is based on material. Even though IT, if there is no chip and no devices, no engine or nothing will happen. It is a material. So the material is very, very important. No doubt, we say this. Even electrical engineering, I know this induction machine and synchronous machine is rotated for more than 200 years. No change in the principle. What is change? It is material. How we can make it efficient, how we can make the proper utilization, and how it can be useful in the different form of applications. So this conference, no doubt, is a nanomaterials. Already, it was very, very important in the 2 decades before, but its application now has come now, and that's why they are talking here. So it is not a physics, it is basically, I'd say, engineering. Now there is no discrimination in the physics and engineering, because the engineering is the outcome, or you can say part of the physics. So the physics is like, of course, the mathematics, chemistry, all the things are inter. So interdisciplinary research are the need of the nation, and we have to come together as how we progress and give a better solution for humanity. Because the technology once we are developing, if it is not good for humanity, so always if we say that we have to, there are many people those are deprived of or disabled, deprived that the technology should succeed. And if that will be the mission, I'm sure this whole nation will rise and grow. So thank you for coming this campus. Those are the first time visitors. Please see it is a lush green campus. It is a very good in the walking in the morning. And this atmosphere is also very pleasant because these days not very cold, not very hot, and then you can enjoy this. And I'm sure this Anurag Srivastava is very good in terms of the hosting the people. So he will keep on feeding you all 3 days, and I'm sure once you are going back, you just visit today, and once after 3 days, it will be 1 or 2 kg will increase. Thank you very much.
Thank you, sir, for gracing this prestigious international conference by your kind words. Now I request Professor Anurag Srivastava for further proceedings.
Thank you, Director Sir, for enlightening us about the importance of the materials and of course how the energy and environment two components are together very important for the society. And it's time, as I said in the beginning, that it's time to honor. And so, as I said, that Professor Rajiv Ahuja last time, 2023, he was not available in person. So let me read his citation first, and I'll request director to do the honor. So before that, let me read. Professor of IIT Roper. He graduated with master's degree in physics in 1986 and doctoral degree in solid state physics from IIT Roorkee in 1991. He worked as a postdoctoral fellow from 1992 to 1995 at Uppsala University, Sweden, where he joined as assistant professor in 1996 and promoted to the position of associate professor in 2001 and professor in 2007. He is also an adjunct professor at Florida International University, USA from 2006, an associate at physics department of Harvard University, USA from 2004 to 2005, a special senior researcher R&D at Foresight, and postgraduate at Swedish Research Council from 2003 to 2009. Professor Ahuja has received several awards and recognitions such as Fellow of Royal Society of Chemistry in 2021, elected Fellow of American Physical Society in 2019, elected member of Kogliga Vetenskap Society in Sweden in 2011, elected member of Board of European High Special Research for 13 years, and Walmart's Prize for 2011 by the Royal Swedish Academy of Sciences, Ballon Lectureship for the APS March meeting 2017 at New Orleans, USA, awarded the Global Initiative of Academic Network by MHRD 2016 and 2018, and awarded the scheme for promotion of academic research and collaboration with Spark by MHRD 2019, Peter Lilly and Sven Theoras Prize in 2005, and Evangelist Medal in 2001. He supervised more than 30 postdoctoral fellows and 33 doctoral scholars and published more than 1,000 research articles in International Journal of Repute. That includes 6 Nature, 1 Science, 25 PNAs, 35 PNL, 4 nanoletters, 4 X chemistry, 3 advanced functional material, 9. So the big series of the publication on his name, and with a total 51,000 citation and an outstanding H plus index of 106. He has 1 patent in spintronics and delivered more than 100 invited talks in keynote. He is an associate editor of Nanoenergy, editor of Nature Scientific Reports, and serves as editor of board of Journal of Material Chemistry and many more. He is a referee of several international funding agencies and journals. It is absolutely impossible to quantify all his contribution and achievement. So with this, we sincerely thank Professor Ahuja on behalf of the scientific community and on behalf of the CANDEE 2024 for the phenomenal contribution and proudly present his honorary citation. Thank you so much for inspiring each of us, sir. So I request Professor Assistant Senior Director to do the honor, please. Thank you, sir, for accepting this honor. In the series for 2024, we have with us Professor Rao. So let me read his citation and request again, once again, our director sir to do the honor. So before that, let me read his citation. So Professor Rao, born in the city of Mumbai, is a pioneer and innovative researcher. After pursuing his BS in physics at the University of Bombay in 1983, he moved to the United States for higher education and completed his doctorate degree from University of Kentucky in 1989. Thereafter, he worked as a postdoctoral fellow at the Institute of Technology, MIT, where he collaborated with legendary Professor Mildred Dressler, fondly known as the Queen of Harvard. Currently, Professor Rao serves as the Robert A. Bowen Andrew Professor in the Department of Physics and Astronomy at Clemson University, USA. He is also the founding director of the Clemson Nanomaterials Institute, where his findings continue to shape the field of nanomaterials. He was also the former associate dean for discovery in the College of Science at Clemson University. Renowned for advancing Raman spectroscopy as a powerful tool for characterizing carbon nanomaterials. He has also developed innovative liquid injection synthesis methods for carbon nanotubes. His current research explores the diverse application of carbon and other nanomaterials in energy harvesting and storage technology. He received several awards and honors for outstanding contributions and lead each one of them. Fellow Materials Research Society, his fellow of National Academy of Inventors, recognized by the Board of Trustees as one of the top 3 faculty members in the College of Engineering and Science, Clemson University, Governors Award for Excellence in Scientific Research, South Carolina, Alumni Award for Outstanding Achievement and Research from Clemson University, Fellow of American Association for the Advancement of Sciences, Robert Bowen Andrew Professor of Physics, Clemson University, is a Fellow of American Physical Society, panel member of the World Technology Evaluation Center to evaluate carbon nanotube manufacturing capabilities in Europe as well as in Asia. Faculty Achievement Award, Clemson University for exemplary leadership. With a robust track record of securing research funding from agencies like NSF, DOE, DOD, NIH, and private industries, and citation of over 56,000, and H-index of over 100. Professor Rao stands as a leading figure in the field of nanomaterials. With this, we sincerely thank Professor Rao on behalf of the scientific community as well as CANDEE 2024 for phenomenal contribution and proudly present this honor citation. Thank you so much for inspiring each of us. Thank you, sir, for accepting this honor. In the series, we have another scientist sitting on the dais here. So let me read his citation, Professor Ajay Kumar Mishra. And again, I will request Director Sir to do the honor. And as I said earlier before that, let me read his citation. So Professor Ajay Mishra is MPhil, PhD, CSI, and FRSC, is a distinguished academic researcher currently serving as a professor in the Department of Chemistry at the University of Western Cape, South Africa. Recognized as a dedicated researcher by the National Research Foundation, South Africa, he has also been instrumental as the director of the Academy of Nanotechnology and Wastewater Innovation in South Africa. In addition to these roles, Professor Mishra serves as visiting professor at Robert Gordon University, UK, Dutch State University, Russia, and Head University of Science and Technology, China, as well as an adjunct professor at Jiangsu University, China, and Wall University of Technology, South Africa. Previously, he held professorship in Durban University of Technology, KIT Dean University, and the University of South Africa. He also served as associate professor and senior lecturer at the University of Johannesburg, where he directed the Center of Nanomaterials and chaired the IEEE Nanotechnology Council South Africa, etc. Professor Mishra has made significant contribution in the area of nanoscience and technology and water research, and over 4,000 publications in peer-reviewed journals, conferences, book chapters, and has over more than 30,000 citations and has a dates of over 50. He has also edited more than 40 books and authored over 80 book chapters with esteemed publishers. His academic influence is underscored by his delivery of 143 plus million and keynote and invited talks at prestigious institutions and events worldwide. Professor Mishra has successfully guided more than 20 PhD students and 12 postdoctoral fellows, and he has earned a place among the top 2% most cited scientists globally from 2019 to 2023 academic year. As per the Stanford University's ranking, he received prestigious titles such as Fellow of Member and Chartered Scientist by the Royal Society of Chemistry UK and Chancellor's Prize for Exceptional Research. His influential work consistently enhances the field's progress and produces high quality outcomes. With this, we sincerely thank Professor Mishra on behalf of the scientific community and CANDEE 2024 for the phenomenal contribution and proudly present this honorary citation. I may request directors to do the honor, please. Thank you so much for inspiring us. So let me do the honor of the director sir and our head of the department. So with this, thank you so much all the dignitaries for accepting these honors, and for further proceeding, may I invite Vani.
Thank you so much, sir. Now, I kindly request all our esteemed guests to occupy the front seat as we are now ready to proceed with the keynote talk session 1 of Professor Rajiv Ahuja.
Hello, hello. Yes, sir. Okay, we can start this morning session. First of all, I would like to thank to Inaugral for inviting me here and the kind hospitality which Professor SNC has given and the way he showed his energy. I am sure that Triple IT and Gwalior will touch the new height. And I'm sure maybe you are already in top 3 in Triple ITs, but I want to see you in top 1. So this is the vision which you should carry actually, and make this is one of the best Triple IT in India. Because Professor Singh also come from IIT, and you know that in IIT we have only 2 I. When you come to Triple IT, now you have to add 1 more I, so you have to work more actually. So this is the thing when you come to a new institution, you have to do that. So when I came to India, so I came only 3 years back, 3.5 years back to India, and I have been offered the oldest IIT of India. Then I thought, okay, if you go in a younger institution, you can do much more rather than going to the older institution. So I accepted IIT Roper actually. And in between, I said, I'm going IIT Indore. Then I said, the minister said, no, you are not going. You are going to Kharagpur. I said, no, I don't want to go to Kharagpur. Then in the end, I end up in Roper. Then he told me that this is a IIT which is very close to his heart. So you should go to Roper. And this is also fit very well that if you want to do something different, you can do in a younger institution rather than older institution. So I accepted IIT Roper to be. And since last 3.5 years, being a director there, actually we are doing very good. And I can tell you that now we have too much funding. Now I always think now we have to deliver. So we are one of the best performing IIT, young generation IITs. And I always say that I don't want to compete with older IITs. So, and our vision should be different to other IITs. So, IIT Roper, we want to grow through research and innovation. So, we don't want to do the other traditional thing what other institutions are doing. So, we want to grow through research and innovation. And this is the motivation. Because when in the younger IITs, you can motivate your faculty members. So this is and your faculty is young, your students are young, and even director is young, then you can fulfill the dreams. And very recently, we have got one of the biggest funding at IIT Roper, when Ministry has started 3 AI projects. One is AI for healthcare, one is AI for edtech, and one is AI for smart cities. So AI for smart city has gone to IIT Kanpur, and AI for healthcare is jointly awarded to AIMS Delhi and IIT Delhi. But AI edtech went to IIT Roper. So we were one of the youngest IIT who got this, and we have received 330 crore for this just only one project, which we have to use next 5 years. So why I have chosen agri-tech also that because we are talking about environment, we are talking nowadays about sustainability. But most of those IITs are working more on technology side. But and as IITs, there was only one IIT who was involved in agriculture, the other say is IIT Kharagpur. So what we want to do, we don't want to do any agriculture. So we want to do digital agriculture. And now you have seen that where in last cabinet meeting, Ministry has announced 14,000 crore, 1,400 crore in digital agriculture. And again, there again, agri-tech is going to play a very important role, and institutions like triple ITs have to play important role when we talk about digital agriculture, whether it's in form of AI, machine learning, or large language model. So we have a signed MOU with now Ministry of Agriculture. Actually, we have not signed, but on 23rd, the PMO is going to highlight that MOU between IIT Roper and Ministry of Agriculture, and to work in the area of agri-tech together with Ministry of Agriculture. So this is you can see that this is the entrance of the IIT Roper. You can see that IIT Roper is situated on the Indus Valley civilization side. So basically, if you see these 4 pillars there, their training is from Indus Valley civilization. So this is the replica what they have found in Indus Valley civilization. And then you combine the ancient knowledge with the current science, so that's what the cubes mentioned. So we are giving the education which is combining the Indian traditional knowledge plus the knowledge which we call the modern science. And the back side we have all the administrative blocks and posters. So as I told you that I work in Uppsala University also. So when I joined as a director, I took a leave from there for 5 years and joined as a director at IIT Roper. So whatever the research what I am showing today, this work is done in Uppsala, and I am still working there. My research group is there, and I have decided I will not take any funding from IIT Roper, or I will not apply for any funding in Indian funding system from myself. So I am not taking any funding. But we are very actively involved in research. As I told you that we want to grow through research and innovation. And I myself is involved heavily in research. And I always tell to my faculty members, if I can do research, why you cannot do research? And then when they say they have too much administration or teaching, but I say we also have a lot of administration. So I can tell you last 3 years, 10% of the publication of IIT Roper is mine. So I'm pushing them also that you have to perform. So when nowadays if you go to anywhere, people talk about sustainability. And this is a kind of buzzword nowadays, AI and sustainability. This is a true buzzword now. And even funding agency like that. I can tell you one incident, actually it was happening in Sweden. And one guy submitted a project and then he said, oh no, this is not a good project. We cannot fund it. Next time he put word AI and ML. Now it's very good. So this is the buzzwords people use, and you put the sustainability. So people like this word, funding agency like this word, and they will find it. But I think we can do a lot, being coming from the AI community or machine learning community, we can do a lot nowadays. And we always say that the AI is going to be there for next 30 to 40 years. So you cannot avoid the AI. So one must have to use the AI for different applications. So what we done at Roper, we have started a program called AI for Bharat. So AI for India. And we have a target to reach all students from any age, any faculty member from any even housewife can learn AI. So we started 2 months back. Now ministry has adopted it, and they asked us also to put on same plus. So we had started 2 months back, and now we already have 10,000 students in AI for all course. We are giving the minor in AI with a 15 credit course, and BTech engineers, or they can use that in their curriculum also. IITs, other IITs can use, triple IT can use it a part of their curriculum, or we can give a certificate them that they have taken a minor in AI from IIT Roper. So that it's an online course, but the exam will be the physical mode, and this exam will be done in all over India level, like we do JEE Advanced with the TCS. So this will be the mission, and we want to reach at least 1 lakh in coming year. 1 lakh students should take this AI. And we say AI X can be anything. It can be civil engineering, mechanical engineering, or even humanities, or even law, medical, anything. So this is 10 credit will be the core AI, 5 will be the application, which will be your specialization. So we are working on that one, and we want to reach those people who cannot get admission in IITs, so they can get this minor with AI. And then we have started another program with IIT Madras. It's also a joint degree program, BSMS program in data science. In data science, and where BS part will be taught by IIT Madras, and MS will be taught by us at IIT Roper, and that will be a joint program between two IITs. So we are talking about sustainability. Pointer doesn't work on this one. So you can see that number 7 is about the clean energy. No, the pointer is not working. Don't move that one. So you can see the number 7 is we are talking about clean energy. This is one of the main topic of this conference also, and I will much more focus on number 17, which is partnership. In India, we are lacking that. We are very individualistic people. We don't want to work with other people. So collaboration is very important, and this kind of platform is very important. When Anurag has a lot of international people here, so you should start a collaboration with them and or with your peers in other institutions. This is what we are lacking. So India cannot grow. India cannot be number 1 economy without collaboration. So we need a collaboration, and this kind of conference is providing us a platform. So when we talk about materials, as already Professor Singh mentioned about materials, and that is another problem in India, we don't talk about materials. We are talking only about computer science. We all want to go in IT, our students want to go in IT, but nobody is thinking to do the core manufacturing industry. If you want to be develop India as a manufacturing hub, we need a materials. But we are not putting focus on materials. So materials should be the key focus. I remember when we were in Europe, we never talk about computer science. We always talk about material science. Material, if we don't have material, how we can develop material? Or how we can develop the industry actually, manufacturing industry if we don't have material. So material is important, and we need everywhere. So you can see that materials, when we talk about energy, we can have materials for power generation in form of the photovoltaics or for wind energies or fuel cells. So we need there also again material. So if you want to go, India wants to go a solar mission, then we need semiconductors. And we need semiconductor for all India. So if you look at the semiconductor, we are not manufacturing chips here. For any semiconductor, most of the semiconductors we are importing there. So we have to develop a manufacturing sector in the semiconductors, and that we are lacking in India. So now with the recent government's effort, there are 3 plants are coming. One in Assam, where we were the knowledge partner when I was the director of IT Guwahati, and 2 are coming in Ahmedabad, one by Tata's and one by Micro. So we will start manufacturing our own chip here, or at least we can start doing packaging. We are not doing even packaging in India. So we always say that if any country will lead the world, the country which will control the semiconductor. So this is the future, and we should think about that. We should be leader in the semiconductor industry. India is one of the biggest manufacturer of mobile phone now, but we are importing all the chips or any even small sensor from outside. So we have to develop our own. So we are also working on batteries also. So this is the one of the part which is written in storage, where we are working with the batteries, supercapacitor, or even the superconducting magnetic storage also. And transmission is very important, because we are talking about solar, or we are talking about EVs, but we are not talking about how we can reduce the energy losses during the transmission. And some part of, I tell you, in Punjab, there is almost 75% loss. So what you transmit and what you get. So if we can save in India, I think on average, if you talk any electrical engineer, they will say almost 50% loss coming from the site to distribution. So we have to, in distribution, we lost a lot. And in Sweden and in European countries, they are going for this mission called smart grid. So there are again people from AI and ML, they are very important when we're talking about smart grid. So if you can save those losses, that is also energy production. I know in Amsterdam there is a big group, he is a professor from ABE, and he always says that I don't believe in solar energy. Why you don't save this 50% losses, and I will solve your problem. So this is another way how we can reduce the losses. One way is that we can make a superconducting power cables. Then we will reduce the. We need a room temperature superconductor. If we have that, we can. So we need materials, and we need materials, advanced material for a sustainable development. So today I will talk about a sustainable economy. What is a sustainable economy? Sustainable economy is a hydrogen economy. Because in sustainable economy, in hydrogen economy, you start with water and you end with the water. And India is going for hydrogen mission. India is going for also for hydrogen, as other European countries like Germany has already started that. They have closed all the nuclear power plants. So they are going for hydrogen. So hydrogen is the future, and that is the future in India also. So here in India, we have a lot of biomass waste, especially in Punjab. And when we are talking about all the winter time, the stable burning issues, so we can generate hydrogen from biomass also. So that's another way to convert biomass into useful product. Now we are talking about green hydrogen, grey hydrogen, many hydrogen. So we are talking about green hydrogen. And India wants to be the biggest producer of green hydrogen. And they want to export to Europe and US. So there was a big meeting, I think last month in Delhi, and on green hydrogen. And they were all focusing that how I can produce green hydrogen at low cost and I can export to the country like in Europe or US. So if you want to develop India as a hub for the clean energy, so we should use that hydrogen which is produced in India rather than exporting using here. Because their plan is that 75% of this hydrogen they want to export. Only 25% will be used in India. So there is a challenge also how to produce hydrogen, how to store also, because that's a big issue. Then especially for mobile application, when you are talking about how we can use hydrogen in the buses and how we can use the hydrogen in the cars, and people are using the company like Toyota, they are using hydrogen as a gas system in a small hydrogen cylinder. So as you know that hydrogen is very light and it's very nasty. So it's interact with the body of the cylinder and it develops the crack and hydrogen can leak out from the system. So we have to avoid those issues also. Maybe you have recently heard a story where a submarine made with a carbon fiber. So they say, okay, hydrogen is interacting with the steel, maybe we can take other strong materials like carbon fiber based material. That's the strongest material, we believe. And in the end, that also busted. One submarine was busted in the sea and nobody was survived. And they were using there also hydrogen, but for the cylinder, they were using the carbon fiber based cylinder. So this is also in the line what Prime Minister has announced in one of the Independence Day speech that mission to make India the new global hub for green hydrogen and the largest exporter. So India is setting up a national hydrogen mission. It's already there was a call this year, and they are making now 5 hydrogen hub for valleys in India, in different parts of India. One in the east, where they are making in Bhubaneswar, and one in the central part with the Pune, and then in the south in Kerala. So they have made, and then in north is combined with Jodhpur and IIT Delhi. So they have already divided the region-wise hydrogen valleys. Because when you're driving a hydrogen, you want to fill hydrogen filling, you need hydrogen filling station. So we want to develop that also. And this was, I already talked about that, this was the initially started. And this is the picture, quotation I always shows. When we talk, people was talking about hydrogen economy, whether it's a new idea or it's a old idea. So this is a quotation from one of the famous novelists. His name was Julius Verne, and this novel is written in 1874, where he said that when the deposit of coals are exhausted, we shall heat and warm ourselves with the water, and water will be the coal of the future. And this is what when we talk about hydrogen economy. So basically, we want to break water into hydrogen and oxygen, and we want to use hydrogen as energy. So it's already predicted in 1874, and this guy was not a scientist, he was just a novelist. So idea was there, and now it's coming to be true. And what is the advantage of hydrogen economy? Basically, the advantage of hydrogen economy is one of the advantages that is very clean, and it's very light. If you look at your periodic table, hydrogen has atomic number 1. So it's the lightest element what we have in this universe in terms of when you look at your periodic table. So it can pack very high volume. This is important? Because if you want to use hydrogen for mobile application, you don't want to make your tanks very heavy. Otherwise, your mileage of your car or bus will go down. So we want in a small tank a lot of hydrogen. So that's the advantage with the hydrogen. You can, in 5 kg cylinder, you can drive your car for 500 kilometers. Just imagine. So hydrogen, when we talk about hydrogen economy, so hydrogen economy basically has 3 pillars. So one is the production, we have to produce hydrogen. Then we have an issue of storing also hydrogen and how we will use it. So production we can do with the biomass or the photocatalysis of the water. You can produce hydrogen, or you can use for biomass, you can generate hydrogen from your biomass. And then you can store also. If you don't want to use for a mobile application, you don't need to store. And then you can have a storage also in 3 different forms. It can be in gaseous form also, it can be in solid state form also, and it can be also in a liquid form. So storage is also a key issue because, as I told you, hydrogen is very nasty. And then you can use in the fuel cells, and for that you can convert the chemical energy to the electrical energy. So as I told you that hydrogen can exist in 3 different forms. One is a gaseous form. So when we use a gaseous form, which we are right now we are using everywhere in the world, and so basically you put hydrogen under pressure. So hydrogen is always under pressure when we put in the cylinder. So you think about when hydrogen is under pressure, it's like a hydrogen bomb. So there are a lot of safety issues. You can also store liquid storage also, but liquid storage also again maybe not that much viable because then you have to cool down your system at a cryogenic temperature. So you spend more energy by cooling it down. And the safest way to store hydrogen is a solid state storage. So I will not going to talk about gaseous storage. Gaseous storage in India, our problem is now that we are importing all those cylinders. We are not manufacturing in India. So we are developing now a cylinder which we can go run maybe 1,000 kilometers. But then we have need a bigger size of cylinder. And when you do bigger size, then you need more high pressure. Okay. So then again, this is again safety issues also. So here we are working on that. Rather, we should use the standard steel cylinder or go for some other composite or other materials which can be more safer to use. So when we talk about when we talk hydrogen for the mobile sectors, so we want a material which can have almost 98% of hydrogen in it. But this is not a criteria. This criteria is a US criteria, where in US the oil is so cheap. But if I can find a material with 2 to 3% hydrogen, that's sufficient to be worked on in India and the Asian countries where oil is so expensive. So when we want a good hydrogen materials, we also want that it should be show the very good thermodynamics, and it has a long cyclability. So it's not like that you charge your battery one time and then you throw away. So you also want to use that system. You can put hydrogen multiple times and you can take hydrogen multiple times from that system. And of course, safety is one of the key issues when people are working in hydrogen. So this is the vision. People working in hydrogen economy, that you can fill your plane with the water and then you can drive the whole world. So that's why I'm saying you start with the water, you end with the water. So this is the vision, and there are a lot of challenges, a lot of issues we have to fulfill, and there are a lot of issues with material science and technology related issues. So again, the collaboration is very important. So here, scientists and engineers has to work together to solve this problem together, and especially material scientists. The other application what we are talking nowadays, everybody is talking about batteries. So we want, what is our vision? That we want a high capacity batteries, at the same time very lighter batteries. See, this is again a challenge. Yeah, if you look at it in this scale, that we want at the same time very high density batteries, but it should be very thin also. So this is again big challenge, and this cannot be only resolved by technology. Again, materials science is going to play a very important role. So how to find and where to find these new materials, and how we can replace this lithium-ion battery. People are talking about now sodium-ion batteries also, but the issue is that most of them are the same. Because in sodium-ion battery, the output voltage is low, because sodium is bigger ion than lithium. So when we intercalate lithium, for example, when we are using electrode of carbon, but we are using LiC6 right now. So sodium ion is bigger, so it needs more space than lithium. So your output voltage is very less compared to lithium ion, if you look at it. And this is I always try to tell people how important this work is. Although Nobel Prize is not given for technology, but nowadays you can see that this year also Nobel Prize is given to AI. And people are saying what AI is not a basic science, but if you read the citation, it says that AI and it's linked with the statistical physics, because you are using a statistical model. So statistical, physical, and together with AI and machine learning, so they have given this year Nobel Prize in physics. And that year, this year, it was given for development of lithium-ion batteries. So if you talk to anybody in Nobel Committee, they will say that the Nobel Prize is given for basic research, but in this time, given to advanced technology, because it's changing the life of the people. So that's the mission when they give Nobel Prize, that it should have an impact on the social life of the people. And this is the slide which I always show it, and this is why collaboration is important. When Professor Singh has mentioned new education policy, multidisciplinary research. So this is very important. So these are the two people who are professor at Uppsala. And Lenin is a guy who has given all the classification of plant. Whatever plant classification, if you are working in a botany, is given by Lenin. So he was a professor at Uppsala in 1741. And the other guy, and the Celsius, you use every day the temperature scale. And he has given the temperature scale what you are using right now. So he was also professor in our department. So they met in one conference like this one, and then Lenin told to Celsius that I heard that you are giving a temperature scale where water is boiling at 0 degree and freezing at 100 degree. So it sounds very awkward that Lenin told to Anders. Anders got an idea that Lenin is right. Although he was a botanist, he was a doctor, he was not a physicist. So physicist got an idea from a medical doctor. And then he went to his lab and he reversed the scale. Now water is boiling at 100 degrees heat and freezing at 0 degree. Think about if these two people has not talked, we will be still using water is boiling at 0 degree. I tell you. Important is the collaboration, and this kind of meeting is a collaboration. I always try to tell my student in IIT, because there is a problem when somebody comes from outside and give a talk, and then you will see that the presence of the students and faculty is very low. वो बोलता है कि मेरे एरिया में तो कोई टॉपिक दे रहा है, he's not giving in my area, why should I go there? And same thing, student always argue that this is not in my area, why I should go there? That's wrong. I tell you, if you go to this kind of talk, you will learn more rather than hearing the people who are working in your area. You get more idea when you go to the other people's conference, other people's talk, then you learn more. And I never go the talk where all computational material science will come. I will never go there. I will go where the experimentalists will be there, so I will learn from them. And we will learn the problem, what the problem they are facing. So this is the advantage we have right now, and government is also pushing. People are talking about multidisciplinary NEP, you have to implement national education policy, and research is the area you can implement immediately. So this is the advantage, and we should use this advantage and to work with each other. And I want to give you one example also. And this is also I talk to our faculty members that we should have a common coffee. And in the morning every day, Uppsala, our physics department is the biggest department in Uppsala University. We have more than 100 faculty members. It's like an institute itself. And we have every morning joint coffee. 10 o'clock, everybody should be there. And this includes not only faculty member and PhD students. And we get a lot of exchange of ideas. So all good exchange, all collaboration are created at coffee table, I tell you. And once I went in a coffee, it was, and then people asked me what I am doing, and then there was an experimental guy was sitting, he said, Raji, what are you doing? He said, then he told me, I have one problem, can you do this calculation for me? And he was working with a Grasser, this dye-synthesized solar cell, and then he said, can we do this electronic calculation, with how we can have this fast charge, this transfer of. I said, I can do this calculation. And then I gave him calculation. Then I asked him, where you will publish it? He said, Nature. And it's published in Nature. Think about it. I went there for half an hour in a coffee. I get one Nature paper. I get many PRL like this. They say, okay, Raji, can you do this calculation? So we do the calculation from them. They are experimental, they combine, and we have a good publication, good collaboration. So don't think that if you're going for a coffee, it's a waste of time. It's also, you can get a lot of information, what you cannot get from by reading yourself the literature. The field I am talking about, computational material science, so it's not a very old field. So you can say that the field started in 1900 when Planck has given this hypothesis. And then main breakthrough came when Walter Kohn has given the density functional theory. This changed. The density functional theory was given by Kohn in 1964, but he got a Nobel Prize in 98. And he got a Nobel Prize in chemistry. I always say that chemists are much more open than physicists. So all the time the chemist was hating the DFT, but they were the one they give the Nobel Prize to Walter Krohn. Walter Krohn was a physicist. So we always say that the chemists are more open, and whatever nowadays we are doing is we are talking about energy research. This is all chemistry. When we talk about material science, this is all material chemistry. So chemists are very open, and you can see there, when you start publishing your paper, you go to any chemical or chemistry journal, they start with the impact factor 5. And in physics, you end up at 5 almost, if you go. So this is how we can work together. You can see the impact. If you work multidisciplinary area, you can have a different impact and high quality papers. And you can make the difference in the sense that we should not do the incremental research. So we should make some impact. And where the country can follow you, not you should not follow, we should not follow to US or Europe. We should make our own area. And we have the biggest intellectual manpower in the world in India. So we should think about it. So this is a question I always ask because engineer cannot answer this question, how we start our car. But as a physicist, I can tell you how you start and you take your car. So this was a paper we published long time back in Physical Review Letter about the relativity and the lead acid battery. There are a lot of things people are talking that Einstein's theory of relativity is wrong, but we also prove that that's right. So we published a paper and we tried to look at the mechanism in the lead acid battery. We are working on lithium ion battery. I don't think we understand even lead acid battery right now. And we are still using it. And every day when we start our car, we are still using lead acid battery. So we start, वो बोलते हैं ना morning में battery वो ठंडा हो गया, वो charge नहीं battery, so then you cannot start your car. So that's why I say how you start your car. You start your car with a battery. And I tell you, most of you are not know how much output voltage of your lead acid battery in your car. Can you tell what is the output voltage of your lead acid battery? Any student who are using car also? So we don't know actually. How many cells we have in one battery? We have around 6 cells in the battery, lead acid battery. And how much voltage each cell is giving, we don't know. And from where this voltage is coming, that I want to show. So when we done this work, we want to publish in Nature, of course. And Nature rejected, it's not general interest. And then when we publish this paper, they write 1 page news and views on this our paper, which is published in PR, this editorial, which was published in PR. And the Economist, this is the economic magazine, they write 2-page article on our research, what we have done. So sometimes you do basic research, it can make insights, what you are getting from your system. So what we done, we try to look this equation, what is happening in your lead acid batteries, lead oxide and sulfuric acid, and we calculate the energy left and right hand side with the quantum mechanical method. And we solve this equation in 3 different levels. And if you are working in the field, in this field, in quantum mechanics, so now we are talking about quantum mission in India, I always say that this quantum mission should be led by a physicist, not by engineers. Because we are reading quantum mechanics from BSc first year. How much quantum mechanics BTech student learn? They maybe study first year and then they forget. But quantum mission should be led by scientists, not by engineers. So this is if you want to be a successful. So if you look at your quantum mechanical calculation, what we do, basically what we do, we solve the Schrodinger equation, which is basically H psi is equal to E psi. H is my Hamiltonian, and Hamiltonian can have a different part. So I have in this Hamiltonian, you can see there are 3 parts. The first term, which is called mass velocity term, and the second term called Darwin term. So third term is the last one, is the spin orbit term. So you don't have to go in detail. You don't need to do. What I want to tell you, how important are the relativistic effect in this. So basically, we have Hamiltonian H, which is including non-relativistic Hamiltonian, plus these 3 terms. And then I can take one by one this term, add it, or I can take away, and I can solve that equation which I told you. So basically, you don't have to go which method I am using, you just go the number. This pointer on this screen is not working. Doesn't work here. You should buy the green one. Green will work. So basically, if you look at the average voltage from a battery in your lead acid battery, from one cell we are getting 2.1 volt. And then you can see that I have done calculation which we call non-relativistic, scalar relativistic, and fully relativistic. Fully relativistic means I took all the terms in my Hamiltonian and I solved. And then you can see the average voltage I get 2.13. This is my calculation. And this is all done in quantum mechanical level without any input from experiment. This is all ab initio calculation. And the experiment you get 2.1. But if I do the non-relativistic calculation, I get only 0.4 volt. So 80% of the contribution is coming to the relativistic effect. So if I don't have those relativistic effect in battery, I will get only 0.4 volt. I need 2.1 volt. So it means I cannot start my car. So I need 2.1 volt for one each cell. And then people were talking because we are using lead acid batteries for long and lead is always toxic. But if you go in the same column of the periodic table, above lead is tin. And we know that tin is not very toxic. Why don't we make tin batteries? If you do the similar calculation, replace lead by tin and solve that equation again, your voltage, average voltage will be 0.4 volt also. Whether you do scalar relativistic or fully relativistic, you always get 0.4 volt. Why? Because tin is lighter, so relativistic effects are not important. So that's why we don't have a tin battery. Because with tin we always get 0.4, but with the lead we can get 2.1 volt because the relativistic effects are very important because lead is very heavy. So when we publish this work, so this was I talked about The Economist. So this was a picture from The Economist where the Einstein is sitting in the car, and you must know that Einstein doesn't have a driving license. So he was sitting in the car. It said that without the magic of relativity, a car's starter motors would not run. So relativity is driving your car. This was from Economist. And there was physical review there that relativity powers your car. And what does nature do? This is from nature. They write, Einstein starts your car. So now you know how you start your car. So Einstein is, if the Einstein theory of relativity is not there, you cannot start your car. And so the same thing, you can see that people are working, jumping in the solar area, solar field. They are working on lead-based perovskite solar cell. Again, we cannot get rid of lead acid battery. Now you want to work on lead-based perovskite solar cell. And I can say 90% people working in anybody is working in solar. They are not working now traditional silicon-based solar cell or dicing. They are all working perovskite-based solar cell, and this is all lead-based. And again, there also lead is the magic. If they make a solar perovskite solar cell without lead, nowadays they reach the efficiency of almost 20%. If they use take out the lead and put just tin there, efficiency is 1 to 2% only. Again, relativity is very important here. You cannot get rid of lead, whatever you do there. So lead is a magic material, and we want to get rid of it also. And so when we talk about, so you tell me, how much time I have? Eh? How much? This is, you are wrong. Huh? Don't give mic to a professor. If you give a mic to a professor, he will not stop. ये गलती मत किया करो कि वो 5 मिनट, वो 5 मिनट लेगा कि वो 10 मिनट लेगा. Okay. So I will finish in 10 minutes. Okay. So this is the we talked about hydrogen storage. Suppose if I want to drive this car 500 kilometers, so size of my tank will be, you can see on my right hand side where I put hydrogen under 200 bar. But if I use a liquid hydrogen, I can reduce the size of my tank. But if I use some kind of metal hydrides, I can further reduce my size of my tank. But these metal hydrides are not the state-of-art metal hydride. Because I say that we want very high weight percent of hydrogen. But if you use lanthanum is very heavy, the weight percentage will go down. But now we have we call complex light metal hydrides, where you can have a hydrogen up to 10 to 15 weight percent, and that can reduce further the size of this tank. So we can see that if we have those materials which have a high weight percent of hydrogen, if you look at in this table, if we take lithium boron hydrogen 4, we can have almost 15 to 16 weight percent of hydrogen in the system. And I say if you give me a system with 3-4 weight percent of hydrogen, that's good enough to compete with oil and gas. But problem is there that if you look at it, there is a little disruption temperature, that is 553 Kelvin. If I want to take hydrogen out from this system, I have to heat up my system at 553 Kelvin, then hydrogen will come out. But I want that hydrogen should come out from the system around room temperature, which is 300 Kelvin. So if I want to use this material, I have to reduce the disruption temperature. So I can use any of these systems. You can say they all have very high weight percentage of hydrogen, but only the problem is the disruption temperature is very high. So we have to heat the system to take out hydrogen. When you heat the system to take out hydrogen, that's not very viable. You spend more energy to take out hydrogen out of the system. So we don't want. We want the disruption should be close to the room temperature. So we have looked many those materials. It can be metal organic framework, which we call the physics of system, where hydrogen is very weakly bound with the surface of the material with the van der Waals forces. And then we have a Kennedy-Zorn system, which is light metal hydride system, where hydrogen is very strongly bound with the system. So we need a lot of energy to take out hydrogen in this system. But in physics of system, hydrogen automatically comes under the room temperature, below the room temperature. So I took one example for a Kennedy-Zorn system. If you take the sodium alanine, so you can see that hydrogen comes from this system in 3 different parts. In first part, we get 3 hydrogen molecules. In second part, we got 1.5, and the rest come in the last step. And important thing is this reaction is not reversible, because I already talked about cyclability. So when we take out hydrogen from the system, we have to put it back also. So these reactions were not reversible. And when we look at the disruption temperature, is very high. We are talking about 180 degrees centigrade. And room temperature is 25 degrees centigrade. So it's a huge. So how I can reduce the disruption temperature, and how we can make this reaction reversible. So, but there was some paper came, and they shown that if you add in this system a catalyst, which is titanium trichloride, all of a sudden this reaction becomes reversible, and the disruption temperature goes down. So we took this as a study and say why titanium is doing this wonder. Why not we should take other materials? Maybe it's even better than titanium. So what we have done, we have done the electronic structure calculation. What we do, everybody do that. So if I take one hydrogen atom from the sodium element H4, I need around 4 electron volt energy. But if I add titanium trichloride in the system, then all of a sudden energy reduced from 4 electron volt to 1.9 electron volt. So I reduce by a factor of 2 the energy if I add as a catalyst. And you were to say that I'm talking about energy, but energy is directly proportional to temperature. You can use formula E is equal to kVT, where K is a Boltzmann constant, you can get temperature out. So you can see that if I use catalyst, I can reduce the disruption temperature because I am reducing the energy. So then we have looked all possible catalysts. So here I have shown something, and I took like 3D transition metal catalyst. And you can see that the hydrogen removal energy is lowest in the green one for the iron. And where you can see that for the titanium is around 0, and further goes down by -3 eV for iron. So if we use iron trichloride as a catalyst, that will work even better than titanium trichloride. And the energy, removal energy is different by a factor of 3, factor of 3. So it means if I am using in sodium alanine iron trichloride my catalyst, I can reduce the further the by temperature by a factor of 3. What this option temperature get off, I can reduce. So catalyst is working. So we can find different kind of catalysts. And then we find why iron trichloride work better than titanium chloride or other like cobalt chloride or manganese chloride. So basically what we looked at, we have looked at distance between transition metal and the aluminum. So these all catalysts are working on the aluminum side. And you can see that the bond distance between iron and aluminum is the lowest for iron. And if you compare on right hand side, I put the hydrogen removal energy, where again it's for hydrogen removal energy also iron trichloride is lowest, and the bond distance is also lowest. So if we can design a material where I can reduce further this transition metal aluminum distance lower than even 2.5 eV or angstrom, sorry, we can reduce the further that dissolvent temperature. So this is one of the way when we do the computation. And what is its implication? So we went to our experimentalists and then we told them that why you have not tried the iron trichloride, and they told me that they are using ball milling technique. And basically in ball milling they were using the same time for milling it as for titanium trichloride and iron trichloride. Maybe iron trichloride need more ball milling time than titanium trichloride. So we asked them, why don't you increase the ball milling time for iron? So when they increase the ball milling time from 30 to 50 minutes, they see that iron trichloride works much better than titanium trichloride. So this is the way, if you work in a collaboration between theory and experiment, you can do wonders and you can guide them. And this is the last example I'm showing for a physics of system where you work metal organic framework. And the problem in this metal organic framework is that hydrogen is weakly bound with the system, with the van der Waals forces. So hydrogen come out below the room temperature from the system. So here I have to increase the desorption temperature of hydrogen in this system. So we took one example which we call the MOF5, and then we looked at similar kind of way how I can increase the desorption temperature. As you can see that here I have written that hydrogen is coming out from the system at 77 Kelvin. Here I want that hydrogen should come out from the system at 300 Kelvin, and how we should do that. So we done the similar strategy. We use a different catalyst. So in this case, I use a lithium trichloride as a catalyst. So I decorate my system with lithium trichloride, and we find out that, and then we done the molecular dynamics simulation, and we look at the pair distribution function. So I have not shown all the details. I can show you in the last that I can increase the desorption temperature by 200 Kelvin and I still have 2.98% of hydrogen in the system. Just by using lithium trichloride. I can have even, if I do further decorate more lithium, if I use in the system, I can have a 300 Kelvin as a desorption temperature, but I still have a 2.8% of hydrogen. So it means in a physics of system also, this idea is working of catalysis. So before GM motor was want to go for a chemistry of system for hydrogen storage, so now they are all working for the physics of system. Or even Toyota is working for the physics of system. Because they think that increasing the desorption temperature is much easier than decreasing the desorption. So they are all working now for solid state storage in the physics of system. So I think I don't have much time. I can skip that one. So I can stop there. So I will like to take questions. So because another example I want to show for lithium-ion battery. So I will skip here and I stop here and I will not take much of your time. Thank you very much.
I request Professor Akbaral to summarize this talk and open for the discussion.
Thank you, sir, for the exciting talk. You brought about the importance of green energy, and most importantly, the thing, although DOE set a very high bar, we should start somewhere.
Yeah.
And you made a very good point that for 2-8% also is pretty good. And then, of course, as we heard even during the inaugural section, materials drive everything. And in that regard, Sir has talked about sodium aluminum hydride, NaH4, and the challenges that we have is the irreversibility of extracting the hydrogen, which is a major challenge. But then again, there is a solution by using catalysts, just as titanium. And then the importance of how modeling actually helps us optimize these kind of processes. So his work has shown that iron, which is much cheaper, can do a better job. Yeah? And then Sir also talked about metal organic frameworks, MOF, which is another emerging or is pretty well established in the chemistry circle. These frameworks have open structures and they can actually drive the kinetics much, much faster. And wherever the hydrogen sits, whichever site, you can put it in quickly and remove it also quickly. So all these are exciting pointers, and his study has shown that you can now have about 2-8% hydrogen at room temperature, which is a very good start in my opinion. So with that summary, let's applaud this talk again once more. Thank you. Do you want me to take a question?
Yeah. Is there any question? You can take one or two questions. Yeah.
Thank you for a nice talk, sir. I have been following your work from a long time. And
You mentioned you looked this paper on MGH.
Yes.
I have not shown MGH.
Sir, being an experimentalist, I have one question in mind. You have shown that this transition pattern in aluminum bond is an important factor for having a good hydrogen characteristic from NaH4. So, but how we can ensure that we reach this particular transition metal and aluminum bonding? Is it related to the size of Fe? Suppose if I have some size of Fe, some nano size, that can give me this bond length, or is it something? Means how can we achieve this particular bond length?
So this can be what I talked today here. This is I talked in terms of the alanites. So all alanites, like even sodium boron hydrogen 4, on this structure materials, I have shown all this LiBH4, or sodium. In LiBH4, I can have even 28%. So it should work there also. Then it will be the distance between boron or the transition metal side, because then we can do there also, we can reduce how much. So basically, I want to show that there is a mechanism that is the catalyst is helping, and why iron is working better because of their bond distances also it was lowest. So in maybe some other material, it could be some other mechanism also. Right? But in this class of materials, this is the mechanism where we can understand. So that's why we were able to design other catalysts, and the experimentalists can find that, because when they do ball milling in a different time scale for iron trichloride, so iron work much better. And this question also, this is very important. How experimentists should know what is the optimal ball milling time? Because if they are using titanium, they know. So then they do titanium is a 30-minute and iron, but they don't know whether should I do iron for 50 minutes or 60 minutes. So again, the computation material science plays very important, because once they tell iron works better And when you see in your experiment iron is not doing good, then I suggested that increase the ball milling time. When they increase the ball milling time, they see the same result. So ball milling, optimization of the ball milling time, because in hydrogen economy, also hydrogen community, especially in the chemical system, they are using ball milling technique when they mix with the catalyst. So that's only way. So then other thing is also, I didn't talk, the defects can play important role. Because when you are doing ball milling, you are putting a lot of energy in the system. So you create a lot of defects. And nature likes defects. So that also has, maybe without using catalysts, you can increase the defects. You can even reduce the receptor temperature. So defects also play very important. In some example, we have seen that if you put catalyst plus defect, it even further reduces the disruption temperature. But answer to your question, for this, like I take a sodium aluminate or this kind of materials with the same structure, I can screen whole periodic table. And I can tell you which one is going to work better. And now we know what is a parameter, or if you can find another system where you can have even below 2.5 this bond distance between hydrogen and transition metal, I'm sure that will be better tested. But it's not easy to generalize the whole system. Did I answer your question?
Yes, sir. Thank you, sir.
So let's thank the speaker once again.
Thank you, sir, for your invaluable insights and thought-provoking keynote talk, which have truly set the stage for the groundbreaking discussions ahead. Now, I would like to request Anurag sir to present the memento as token of our appreciation for their valuable presence and contribution, followed by vote of thanks.
So this is the closing of this inaugural ceremony and the keynote session. So let's thank the speaker once again, as well as Professor Apparao, who has summarized this talk, Professor Ahuja. And thanks everyone for joining the session. Let's join for the high tea in the convention center. We'll move there and we'll also have a group photograph there as well. Thank you once again. And for further sessions, we'll have in the hall 1 and hall 2 in the convention center only. Thank you all.